So I'm excited that we have Dana Ramadan here today. After quite a long break with the seminar, and we just talked about it. Like there were a couple of holidays in the last Mondays that we scheduled, but also in the next Monday that is scheduled, we have President's Day in 2 weeks. But after 2 weeks, we will continue with Alla Drobrück looking at ex vivo vessels and so on. So Dana today will present her work on high resolution MRI at 9.4 Tesla. Dana is a PhD student with biomedical training at the Max Planck Institute in Tübingen in Germany, where I think you're working with Klaus Scheffler and Jonas
Yes.
Bause.
Yeah.
You are working on gray matter segmentation and mostly at 9.4 Tesla data, but you also care about vessels, which is something that I care about a lot as well. And I asked you to talk about that part, specifically the vessels and their influence on fMRI. And the title is Macrovascular Contributions to Resting State fMRI Signals, a comparison between EPI and balanced SSFP at 9.4 Tesla. Please.
Okay. Thank you so much for the introduction, and thanks for inviting me. And thank you all for joining. All right. So I will be talking about my paper here. Um, um, that was actually published last year in Imaging Neuroscience. So I'll start at the very beginning. And as Renzo said, I care about the vessels. And I mean, everyone should care about the vessels because we all know that the brain does not have an energy reservoir, which means um, we have a neurovascular coupling that leads to a hemodynamic response, which is for us the basis for fMRI or bold fMRI, which we actually need to see something in fMRI. So yeah, and the thing about the vessels is that have if you simulate them as infinitely long cylinders filled with paramagnetic substance, then you can see that they produce perturbations around them, and these magnetic field perturbations, they are highest when these veins are or these cylinders in this case are perpendicular to the main axis of the magnetic field. Now you can also see that here. So in A and C, the veins are or the cylinders are perpendicular to B0, but in C, the simulated cylinders are parallel to B0. So if they're parallel, then we don't see any mag magnetic field offsets. But then in our paper, we talk a lot about the cortical orientation. And why is that so? So we have large veins on the cortical surface, and these large veins, they follow the cortical curvature very tightly. So we say that the cortical orientation is a good estimate for these large surface vein orientation. We can also take this formula and kind of simplify it and say, okay, so our extravascular frequency offset um, is very proportional to sine square of nu. In this case, nu you can see up here. So nu is the angle between B0 and the vessel itself. But we're looking at theta B0 here. So the cortical orientation, which is in 90 degrees to our vessels, meaning that our extravascular bold signal change should be proportional to cosine square of theta B0. And we care about this extravascular signal a lot because it dominates at ultra high fields. Now we have the sequence that was mostly used or is mostly used for bold fMRI at ultra high field. And this sequence is very much biased towards large draining veins. And you can see that these large draining veins, again, I'll repeat it, they're on the surface. And what else is there? Yeah. And then you can also see a bias towards the cortical surface of your fMRI signal amplitude. Yeah. Talking about sequences, I will start with a T2 star weighted gradient echo EPI. So yeah, as I said before, it's biased towards large draining veins. This is bad because then we're not very specific to brain activation. However, it is very much used because it's very sensitive to the bold signal. Then there's also spin echo EPI. As you can see here, gradient echo EPI is sensitive to all vessels, but is biased towards large draining veins, and spin echo has a sensitivity to smaller radii. However, spin echo EPI is unfortunately not very feasible at 9.4 Tesla due to SAR limits. So then we have a third bold sequence, which is bSSFP, and it has a T2 over T1 weighted signal, which gives us a kind of a spin echo-like signal. And there are simulations on that looking at exactly this here, and you can see the gradient echo behaves as the gradient echo here, spin echo as the spin echo, and then the bSSFP also has some kind of excuse me. It is also sensitive to smaller veins and has a specific sensitivity. So then, can we use the cortical orientation to investigate a sequence's vessel sensitivity? And what do we expect for a sequence that is less sensitive or more sensitive to large veins? Well, large veins are on the cortical surface, and they follow the cortical surface tightly. So if we have signals mainly from large veins, then we should have a cortical orientation dependence. But if we are more sensitive to the capillary, which you can see here is very much randomly oriented, then we shouldn't get a cortical orientation dependence. So we wouldn't also be the first ones to do this. So actually there is work by Gagnon and colleagues which shows the difference between here gradient echo and spin echo EPI on their cortical orientation dependence. What you can really appreciate here is that gradient echo EPI has a very strong dependence with the highest bold signal change around 0 degrees, which is in this case when the veins are perpendicular to be 0. So exactly what we expect. But in spin echo EPI, we don't have this kind of dependence. They did this in simulation, as you can see up here, but they also did some experimental work on that. So you can also appreciate the cosine square function that they fitted here, which I talked about in the very beginning. Also in our group, there was work looking at gradient echo, spin echo, and bSSFP, cortical orientation dependence. And what you should note here is that the y-axis is not the same over all 3 plots. And in this case, they also looked at some vessel networks and different cortical layers to see the cortical orientation dependence in these layers. Then in the last work that we also kind of try to replicate in this paper is the work by Wisman and colleagues, where they are looking at the resting state fMRI signal, and they're calculating the coefficient of variation, just like in our case, and they are plotting it on theta b0, which is the cortical orientation. So they see that there's a high cortical orientation dependence especially on the cortical surface, and then moving away from the cortical surface, this diminishes. And here, yeah, this is already white matter. So looking at these 4 plots, you see that it already goes down this orientation dependence, which is expected because you're kind of also moving away from these surface veins. All right, so coming to our methods, I mean, yeah, this is a bit, I think this is a bit too much, so I'm gonna kind of walk you through the methods here. Of course, we started with data acquisition. We had 5 subjects, and 5 subjects were measured in 3 sessions each. In the first session, we had 3D bSSFP, which was 4 runs of 3D bSSFP, 4 runs of 3D EPI, and 1 run of 2D SMS EPI. We chose 1.1 millimeter isotropic, which is rather big, because this is what also Wisman and colleagues used in their paper. Also note that the 2D EPI has a higher slice coverage than the 3D sequences. Then we also had an MP rate, which you can see below here. And in a second session, we tried to kind of see the repeatability of the data. And in the third session, we acquired multi-echo gradient echo, multi-echo gradient echo, sorry, for vein maps, which I will talk about later. So first, the functional data. So this is the part of the plot. What I want you to note here is, or what is important is that we co-registered all the anatomical data to the functional data. So to actually have the least interpolation of the data possible. And then after that, we calculated the coefficient of variation, which is 1 over the effective TSNR. And this we use as a measure for signal fluctuation. This is the same measure that also Wisman and colleagues used. Okay, coming to the anatomical data, we just used a very normal pre-surfer pipeline, and then we calculate the orientation on each surface, which you can see here. And then we calculated that in the volume to actually be able to compare it later. And then in the end, we also had cortical depths, which we looked at, but the depths were calculated in Laney, which you can appreciate here. All right, then I'll start on with the results. So first, the orientation dependence results. We have the coefficient of variation on the y-axis. On the x-axis, we can see theta b0, which is, again, the cortical orientation. We see the effect in the entire cortical ribbon here. So, and this is for 3D bSSFP, for 3D EPI, and also for 2D EPI. We see an orientation dependence in 3D EPI and 2D EPI, but very less so or no orientation dependence in 3D bSSFP. Also, what we can see here is that the highest fluctuation is at theta b0 around 0 degrees, and this is because the veins are here perpendicular to b0 here as well. We looked at that in the different cortical depths, and here you can see depth 1, depth 2, 3, 4, and 5, and you can really see that the orientation dependence goes down with when you're moving closer to the white matter.
Can I
This
ask a
effect
quick question?
Of course, yeah.
So why do you think 2D EPI has a smaller orientation dependence than 3D? They're the same mechanism, right?
Yes, that's true. And maybe I can answer your question in the end of the talk. Is that
Yeah,
possible?
sure.
Because I also have a slide to that in the end.
Okay,
I can show
thanks.
it. Okay. Um, all right, where were we? Yes. So no such effect is seen in bSSFP, which maybe points to a less dependency on the large draining veins and more so of the micro vessels. Then we looked at the depth dependence. So we plotted the same data. So the coefficient of variation again, now not normalized and in different cortical depths. So depth 5 is of course is here closest to white matter, and depth 1 is closest to CSF. And what you can see here is that the values between all three sequences are somewhat similar. So that means we can compare them. And then the coefficient of variation was plotted relative to the deepest layer. And what you can see is an increase towards CSF, which you expect, right? In EPI, you see that in both EPI sequences, but yeah, more so in 3D EPI. And then for 3D BSP, actually, we have a kind of an inverse behavior, uh, which maybe yeah, which yeah, which maybe means that we have higher fluctuation in deeper layers. But yeah. What we can also see here and appreciate is what we saw in the figure before, is that if the orientation is perpendicular, so the black dots, then we have a higher depth dependency than when the orientation is parallel of the veins.
Could I ask about the kind of these arbitrary units? Is this in MR units, or I'm trying to think how much of these shapes can be explained by just thermal noise? Like in balanced SSFP, you have a 1 over T1 weighting, so you have less signal at the surface. Or like for
Yeah.
3D versus 2D, why is 2D higher than 3D? Maybe because 3D has higher SNR and therefore a less kind of the relative fluctuation compared to the signal is different. Does it make sense? Or
Yeah, it does make sense. That's why we also looked at the mean and the standard deviation of the signal separately. I would have to in the let's see. Or I can show it to you in the end as well.
sure.
Then I don't jump around too much. Okay. Exactly. So yeah, we also looked at the mean and standard deviation exactly for that reason, because they have different weighting. Yeah. So yeah, the here I just wanted to show that okay, this is the work by Wisman and colleagues, and they have the coefficient of variation of the same or a very similar to the EPI sequence on they plotted on the cortical orientation. And I mean the only difference between these two plots is kind of here they are normalizing on the peel surface while we are normalizing on depth 5, which is the deepest layer. But what you can appreciate is that the curve is very similar, and that even cortical orientations that are higher are also have a higher or have a lower cortical orientations that are higher have also a very similar profile in both sequences or both plots. Yeah. So, and then we also have the last part of the figure that I didn't talk about, which is the multi-echo gradient echo part. Here we, from this image, we calculated a vessel map, and you can appreciate the vessel map here. And from that, we calculated a vessel distance map, which we essentially use in the end. Here you can see it on the gradient echo image. Yeah. Then we took this vein distance map and we kind of binned it. So we had values between 0 and 0.71 millimeters, which are in the veins or very close to the veins. Then 0.71 to 1.41 millimeters in red, which is a bit further away from the veins. And then green would be 1.41 millimeters to 2.12 millimeters. And we just wanted to see how the cortical orientation dependence changes when we move away from the veins. So what do we expect? We expect that when we're moving away from the veins, that this cortical orientation dependency actually decreases. And this is what we see in the entire cortical ribbon, but we also see it in all cortical depths. More so in 3D EPI than in 2D EPI, and I will come to that maybe later. And then the depth dependence, I mean, same plot as before, just now only the mean of all subjects is plotted and how far away we are from the veins. And you can really see that that this depth dependency decreases when moving away from the veins. Okay, but what about partial volume effects? I mean, we also have very large voxels, right? I mean, for depth or layer analysis, this is a bit big, 1.1 millimeters. So we realized that, and then for two subjects, we also acquired 0.8 millimeter isotropic data, which were in the same session as the 1.1 millimeter data. And here are the results for the cortical orientation. And you can really see that, so 1.1 is the mean of two subjects. The blue line is the mean of two subjects for 1.1 millimeters, sorry. And the red line is the mean of two subjects for the 0.8 millimeter isotropic voxels. And what we can see here is that yeah, basically there is no difference between whether we have a 1.1 isotropic or 0.8, which is, I guess, good for us. But yeah, so we also show that in different cortical depths, and even moving through the depths, you can see that there is not a huge difference between both voxel sizes.
This is kind of surprising, right? Like the angle that you're looking at, the theta, kind of it seems that that the curves only make sense if you are dominated from the pile vessels and not the intracortical veins, right?
Yeah.
So anything like, I guess it could be that even with 0.8 you have the blooming effect from the surface. Or would you think that maybe it's not the resolution of the acquisition, but it's basically the resolution of the segmentation accuracy that might be driving this? That basically you're taking the entire brain, right? So if you don't go in manually, like we usually do for small patches, that there might be just blurring at the order of 1.1 millimeter, even at the 0.8 millimeter acquired data due to segmentation, so that it's not kind of partial voluming of true voxels, but partial voluming of the layer alignment with respect to the cortex or something.
Well, yeah, well, that might be, but I think I mean we did some manual adjustments as well for the segmentation. The problem is that sometimes, as you said in the beginning, I mean, sometimes also when we're calculating the cortical orientation on the surface, then we have some kind of interpolation that we don't take into account, right? But what I think my point here is basically just like, even if I acquire 0.8 millimeter functional data, I still don't get very different results. Yeah. Mm. Mm. But yeah, Yeah, I think, yeah, that's it. So just to sum it up, we investigated the cortical orientation and depth dependence of three sequences. We saw the highest dependence on the cortical orientation for 3D EPI, followed by 2D EPI, with the highest signal fluctuation when veins are perpendicular. Also, we saw a high depth dependence of 3D EPI with the highest fluctuation on the cortical surface. No cortical orientation dependence, and also inverse depth dependence of bSSFP was shown. However, I'd like to note here that bSSFP is very much SAR limited and very slow compared to gradient equi EPI. And what we saw is also that with increasing distance from the veins, um, the the dependence of the cortical orientation and the depth dependence, both of them changes and gets lower, but no such effect was seen on bSSFP. So we hypothesize, or we say that maybe bSSFP is more sensitive to smaller veins, and thus maybe a more specific sequence if you want to do both layer fMRI at ultra high field. But yeah, I mean, at this point, of course, future work is needed with task-based fMRI. We're doing here resting state fMRI. Just to note that again, and maybe, yeah, we definitely need task-based fMRI to prove this higher specificity of bSSFP. And with that, I would like to thank everyone who worked with me on this paper, and also the funding sources, and thank you for your attention. Yeah.
Yeah, thanks. Maybe we can jump right into Birkin's question. Yeah.
Exactly. Yeah. Okay, so I kind of felt like this is coming. So I prepared a slide on the difference between 2D EPI and 3D EPI, and also we try to discuss that as much as possible in the paper. So 3D EPI is more susceptible to physiological influences than single-shot 2D EPI. And this is because you're always repeating the excitation of an entire slab for encoding along the slice direction. And so this is the first thing we looked at, so the physiological noise and how that influences our data. Wait, I don't see my pen. Exactly. So, and what we kind of see is, so the green one is temporally smooth, which is, the green line is temporally smooth, which is what also Wisman and colleagues did. And the red one, the red line here is the mean when you're when we did retro I-core. So after we did retro I-core, which we don't use in the paper. And then what you can kind of appreciate is, so first of all, when you're looking at the blue line and the red line, the effect is higher, so the cortical orientation dependence kind of decreases more in 3D EPI than 2D EPI. Now let's look at it once again. And also, if you're comparing the temporal smoothing, so with the green line, then the effect is very much similar between the 3D EPI and 2D EPI. So we kind of say that it may be because of these because of this physiological influence. We have this discrepancy between 2D EPI and 3D EPI. Then we also have motion. So there's this movement of the tissue border in 3D EPI. So what we did to test this is we kind of did a motion regression. And then after motion regression, what you can see on the right side, so red is just realigned, and then blue is realigned, and then red is realigned with motion regression. And you can really see that when you do the motion regression, then you also have kind of a higher similarity between both sequences. And in this case, we did that only, I think, for not for all subjects. So I think it was just one subject that we did that for. So it's also not a lot, but yeah, this is already showing that if you're doing some kind of analysis, this can also give you, of course, other results. It doesn't, however, change what we're seeing, the cortical orientation dependence and also the depth dependence. I hope that answered your question.
So you think it's basically physiological and no new science, basically, which would have been also exciting.
Sorry, again?
So it's mostly physiological and there is no new science, like no new biological stuff going on that you're seeing with 3D instead of 2D.
I mean, I would say it's kind of a physiological and motion. The reason for it is physiological influences and also motion. And you could see that also in the different slices. So if you're moving inferior, then you can also see more motion of these of the tissue borders as well. So it's also because of kind of the physiological influences.
But it also means that if you do a task now, basically you have something that's not aligned with your physiological noise, that 2D and 3D might look much more similar. Because you're very sensitive to this physiological noise because you look at the overall variation. You're not look at the variation that follows your design, right?
Exactly. So you're comparing two conditions, and then you have you have less of that.
Yeah, although your z-scoring of your task will be crappier with the higher physiologic noise, right? So I'm not sure that solves the problem. What would solve the problem is going to a very much higher spatial resolution, so that you're thermally noise dominated, and then looking at the orientation dependence.
Yeah,
but I have
the 2D and 3D difference might be partly explained by the thermal noise, right? Like in 2D,
it could be. I mean,
this offset it's just independent of orientation, right? And then
I mean, you're probably at 9.40, you're in some intermediate regime, probably. So you have some mixture of the two. But I have a question about the balanced SSFP. So the TR, I think, like from your paper, if I remember, is like around 3 milliseconds or something like that.
Yeah.
So the inverse of that is 300, about 300 hertz. So your SSFP bandwidth is relatively small, which means you probably have lots of places where you have off resonance. And certainly the vessel orientation, which will change frequencies, will create an off resonance effect that's variable, which, I mean, you're not actually seeing, which is very interesting. So I'm surprised at 9.40, like you do this on resonance, right? So you just do your SSFP one frequency, and that frequency is on the water, right?
Yeah, I mean, we hope that we're always on resonance, but we try to, I mean, shim as much as we can, so we are on resonance, yes.
Yeah, but I guess I'm surprised that you don't have banding artifacts.
Well, we try to push the banding artifact outside of our imaging imaging slab. So I mean, in this case, we don't have the bandings in here, as you can see in this slide. I mean, there's no bandings in here, but I mean, mostly you get some kind of bandings, but we try to push them outside of our imaging imaging slab. Yeah.
Okay, I mean, you also, if I remember from your paper, you used an angled volume that's well above the sinuses. I can see that here in your slices. So you're kind of out of the area of high, gross susceptibility.
Yeah. I mean, so back to the wait, where was it? Yeah, exactly. This is the slice orientation that we chose is sorry for jumping. Yeah, this one. So
Oh yeah,
yeah. So you
Okay.
can you can see that this is the
Could you say more about this multi-echo GRE, what you did there, and kind of which kind of vessels do you see? How big are they, and was it needed to have an entire session just for that, or how long does it take?
No, it was just no, it wasn't that we needed a third session for that. Actually, we tried to do it in the second session already because we didn't have so much to cover in that. So it definitely worked out in the second session. However, we changed something in the protocol. I mean, I didn't. Jonas changed something in the protocol in the imaging protocol, and so this led to us making a third session with each subject, which also that's why we also dropped one subject in the process because they weren't eligible for measuring anymore. But I mean, I couldn't tell you too much, however, about how exactly what was done. But what I know is that from the multi-echo gradient echo, he calculated a SWI image, and then he had this German vessel filter applied to it. And then he got the vessels and also manually corrected them. And then from these vessels, he calculated, I think, the Euclidean distance then from the vessels to get the vessel distance map or the vein distance maps.
Gotcha. And this is kind of a thinner slab then, based on the distance map.
It's actually the slab is as big as the so this one. This is the slab I use, so it's as big as the SMS EPI slab, or a bit bigger than the ones used for 3D for the 3D sequences.
Gotcha. Cool.
Yeah.
Are there any other questions?
So what would you consider the primary contrast mechanism for the SSFP?
The primer, do you mean like the weighting of the signal, or
Yeah.
So I mean, I'll go back to the. So the primary or the primary weighting of bSSFP is it's a T2 over T1 weighted signal. However, I don't have the signal equation here, but yeah, I mean it's a kind of a gradient echo-like sequence, but it gives a spin echo-like signal. This is what they also explain in this paper by Scheffler and Hennig. Yeah, so but I don't know exactly what you're referring to, or did that answer your question?
Well, I mean, that T2 to T1 ratio for bSSFP depends very much on the TR and the TE.
Yeah.
So, if the TR becomes very long, then it's actually more T2 star weighted. If the TR is very short, and I never think about this at 9.4T. That's why I'm asking.
Yeah.
Where are you with respect to T1's obviously longer at 9.4T than what most of us are used to thinking about at 7T.
So exactly. I mean, so what we're trying to optimize here is two things. So we're trying to optimize that we don't get bandings. That's the first thing. And also we're trying to optimize with the TR, we're trying also to optimize that we get that the bold effect is also captured. So these are these two kind of limits that we're trying to optimize, and that's why we chose this the TE and TR like that for this sequence. Yeah.
Is there an intuitive explanation as to why SSFP behaves like spin echo or kind of in between? Like, where does that mechanism come from?
Um, well, I think, yeah, I think I mean, it's not intuitive. Yes, because I mean, I still find it very complicated. So, um, I yeah, I wouldn't have an intuitive explanation right now. Sorry.
It's okay.
The 2D and the 3D EPI, they do have different T1 weighting as well, right? For one, you have constant low flip angle, whereas for the other one, you have every. So,
Oh yeah, yeah, I wanted to answer your question as well, right? Or to show you the mean and standard deviations of the signal. Do I have that anywhere? Yeah. So yeah, I mean we do have a different kind of contrast if you're looking at the mean image for EPI and 3D EPI and 2D EPI kind of yeah, we get a very linear kind of function for CSF, but we don't see that in 3D EPI, whereas the standard deviation, so the fluctuation also gets much higher, where 3D EPI and 2D EPI less so. So maybe were you referring to this kind of to the weighting of the signal, so the mean of the time series, or?
yes, yeah, like so. For example, like the mean, the mu here, for 3D and 2D looks different. But I also guess it would look less different if the 2D and the 3D would have the same coverage, right? Because then you have the same, like the TR between the excitation pulses would be shorter. And I guess in the bottom right for the 2D, you have a more non-linear increase as for the 3D. It's just that you're dividing it with a.
But I think for the paper we removed the more slices at the top and the bottom for 2D EPI, because we had a higher slice coverage. So in the end, what we looked at was the same coverage, but what we acquired was more.
Sure, yes, makes sense. It's more that if you would have the same number of slices, the TR, like the time between excitation shots for any given slide would be different. Therefore, the T1 weighting would be different. Therefore, the 2D might look like the mu of the 2D might look a bit more than the 3, because you would have like the CSF and the long T1 layers would be saturated more, like they are for the 3D. But I guess if you would have a different protocol on the 3D as well, right, it might look different, because then the 3D, like if you would have only like a very few slices, maybe it would be like given the coverage, the 2D and 3D kind of merge anyway, right, and they are the same sequence. It's just, I was more referring to the motion results that you showed. So I was wondering whether 3D EPI has a different gray matter, white matter, gray matter CSF contrast, which here maybe it's harder to tell, because we only have gray matter. But I guess in 2D you actually do have a stronger gray matter CSF contrast, right? So any kind of B0 changes you would expect to be stronger in the Y direction, like in the phase encoding direction for 2D than 3D, I guess. Based on the mu, based on the mean, right?
Yeah, I mean, I'm so a little confused because I'm not, I should go back and read your paper, but in the Scheffler approach to balanced SSFP, I think the idea was you actually put the center frequency a little bit to the right of water, so that you're actually in the transition band of the SSFP.
But I mean, this is kind of how the work started, right? And then other people.
But in the Carla Miller approach, you actually do it on resonance, right?
Exactly, and we're kind of doing the Carla Miller approach here.
Okay, so it's just the frequency distribution changes with bold, and you get a change in the phase, which in bSSFP is very sensitive to, and that's your fundamental contrast mechanism. So
Exactly.
it's
I mean, I
still
have,
T2 or T2 star. I mean, it's susceptibility weighted,
yeah.
but it's different
Yeah.
mechanism than I'm used to
Yeah,
thinking about.
you're talking about this one here, right? So
Yes, exactly.
you're exactly. So you're talking about like that if you're in the transition band, then you kind of these are your banding artifacts kind of, and then if you're in the pass band, then you have a difference between. I mean, this is sorry, this is simulated for 1.5 Tesla. It was simulated for something else, but that's why it's so different. But yeah, I think the difference should be larger between arterial blood and venous blood. But this is just to showcase a bSSFP profile, how it looks like, and what Ravi is talking about. So yeah, so this would be the transition band, and this was how the method kind of started. And then, but now, yeah, mostly people use the pass band to do bSSFP bold fMRI. Yeah.